In the early years of the Cold War, the United States relied on a simple equation for aerial reconnaissance: fly higher than the enemy's weapons could reach. The Lockheed U-2, known as the Dragon Lady, was built for this exact purpose. But its design contained a critical flaw. Those massive, straight wings were optimized for slow, high-altitude loitering. It was essentially a powered glider operating at subsonic speeds, making its flight path entirely predictable to Soviet radar operators. That predictability caught up with the CIA on May 1, 1960. Soviet forces shot down a U-2 piloted by Francis Gary Powers, proving that extreme altitude alone was no longer a guarantee of safety. The weapon responsible was the Soviet SA-2 surface-to-air missile. The SA-2 is a radar-guided anti-aircraft system capable of tracking targets and detonating in the U-2's cruising altitude. The U-2 shootdown confirmed what intelligence analysts had suspected since the late 1950s. The vertical buffer zone was gone. To survive inside contested airspace, the military needed a new platform. It had to maintain that extreme altitude, but combine it with a kinetic velocity so high it could literally outrun the surface-to-air missiles fired at it. The task of building this aircraft fell to Lockheed Corporation's Advanced Development Projects Division, a clandestine group better known as the Skunk Works. Led by Clarence Kelly Johnson, this small team was tasked with solving the exact vulnerabilities of the U-2 he had previously designed. Under the codename Project Archangel, the mandate required sustained flight at Mach 3.2 at altitudes exceeding 85,000 feet. Mach 3.2 is approximately 2,400 miles per hour, or more than 3 times the speed of sound. Moving at those speeds introduces a severe physics problem called the thermal thicket. When an aircraft travels at Mach 3, the extreme friction and pressure physically compresses the air against the airframe, generating heat much faster than it can dissipate into the cold, high-altitude atmosphere. Standard aviation materials fail under these conditions. Aluminum, the standard metal for aircraft skin, begins to lose its structural integrity and melt under the continuous 600-degree Fahrenheit thermal loads generated at Mach 3. Solving this required the Skunk Works methodology. Kelly Johnson operated with small, highly empowered engineering teams with minimal bureaucratic oversight, allowing them to rapidly prototype solutions to seemingly impossible mathematical hurdles. The resulting SR-71 Blackbird is a first-principles engineering solution. Every structural quirk of the airframe exists as a deliberate thermodynamic mechanism to keep the plane from tearing itself apart. Because the continuous friction of atmospheric compression at Mach 3 turns an aluminum airframe soft, Lockheed had to find an alternative. They chose titanium alloy. Titanium offers a rare combination in metallurgy. It withstands extreme temperatures while maintaining a very high strength-to-weight ratio, making it the absolute requisite material for the Blackbird. But titanium is notoriously difficult to machine. Its extreme hardness routinely shattered conventional drill bits, forcing the engineering team to invent entirely new tooling and machining techniques just to shape the parts. Welding the metal presented another severe challenge. Even minor exposure to ambient oxygen during the welding process would cause the titanium to become brittle and shatter. Welders had to work in specialized chambers flooded with argon gas to shield the metal from the air. Ultimately, over 90% of the SR-71 structure was built from titanium. Ironically, at the time, the largest global supplier of titanium ore was the Soviet Union, forcing the CIA to set up a network of front companies to covertly purchase the metal used to build a spy plane directed at Moscow. Even with titanium, the massive heat of supersonic flight caused the metal panels to expand and warp. To counter this, engineers used a corrugated skin design featuring tiny ridges rather than a perfectly smooth surface, allowing the metal to absorb the thermal stress without buckling. Conquering the thermal thicket required the invention of an entirely new discipline of aerospace manufacturing and metallurgy. The extreme heat generated at Mach 3 causes a massive physical shift in the airframe's geometry. As the temperature rises, the entire titanium structure expands in length by 3 to 4 inches. If the skin panels were bolted tightly together like a conventional aircraft, this sudden expansion would cause the metal to warp and tear mid-flight. This animated cross-section shows the solution. The skin panels were designed with large expansion joints. These deliberate gaps give the metal the physical space it needs to grow and shrink as the temperature rises and falls. This thermal expansion created a crisis for the fuel system. Traditional aircraft use rubber bladders inside the wings to hold fuel, but the Blackbird's internal operating temperatures would instantly melt them. The compromise was to use the aircraft's titanium outer skin as the actual walls of the fuel tank. Inside these tanks, the plane carried JP-7, a specialized high flashpoint jet fuel designed specifically to handle extreme heat without spontaneously combusting. Because the fuel tanks are the outer skin, and the skin is built with those expansion joints, the SR-71 famously leaked fuel all over the runway while parked. The tanks only sealed shut once the aircraft reached high speeds and aerodynamic friction expanded the metal. While dripping jet fuel sounds incredibly dangerous, JP-7 is so chemically stable that you can drop a lit match into a puddle of it and it will simply extinguish the flame. To actually ignite the engines, the aircraft relies on a separate chemical payload of triethylborane, which explodes upon contact with the air. Every apparent imperfection on the ground, from the corrugated skin to the dripping fuel, was the exact mechanism required to keep the aircraft intact at Mach 3. While kinetic speed was the Blackbird's primary defense, it also relied on an early form of signature management, reducing its visibility to enemy sensors long before the modern concept of stealth was formalized. This diagram shows the design team's physics paradox, trying to hide an aircraft that features a massive 3,200 square foot wing area. By carefully manipulating the airframe's geometry, engineers managed to reduce its radar cross-section down to approximately 10 square meters, roughly the equivalent of a small single-engine civilian plane. A key element in this reduction was the use of chines. The chines are the sharp, tapering edges running continuously along the sides of the fuselage. They provide aerodynamic lift at high angles of attack, but they also serve to physically deflect incoming radar energy away from the receiver. Furthermore, the two vertical stabilizers on the tail were canted inward. This specific angle minimized the amount of radar energy bouncing back when the aircraft was tracked from the side. The skin itself incorporated early radar-absorbing materials. Engineers built specialized sawtooth-shaped structures into the edges of the aircraft, filling them with composite materials designed to trap and dissipate radar waves rather than reflect them. Even the exhaust plume was a radar vulnerability. To mask the massive return generated by the engines, the fuel included a cesium-based additive called A50. This chemical ionized the exhaust gas, altering its electrical properties to disguise the signature on enemy screens. The SR-71 was never perfectly invisible. Its invulnerability was achieved by pairing deliberate structural shaping with a top speed that rendered interceptor missiles mathematically useless. This animation illustrates how the SR-71 did not emerge fully formed. It evolved directly from the CIA's Project Oxcart, which produced a slightly smaller, single-seat precursor known as the A-12. The A-12's success led the Air Force to explore multiple branches of the platform, including the YF-12A interceptor. This variant tested the airframe's ability to carry heavy internal radar arrays and AIM-47 air-to-air missiles. The final SR-71 design required a structural compromise. Engineers traded a fraction of the A-12's maximum speed and altitude to elongate the fuselage, making room for a reconnaissance systems officer and a significantly heavier payload of side-looking radar and signal intelligence sensors.
The SR-71 became the definitive variant because it successfully balanced the raw physics of extreme performance with the practical necessity of gathering complex, multi-sensor data over hostile territory. Despite its performance, the Blackbird eventually fell victim to its own analog architecture. Its cameras required physical film that had to be downloaded and processed after the plane landed. By the 1990s, military strategists prioritized the instantaneous digital data streams provided by modern surveillance satellites. After the Air Force retired the fleet, NASA utilized several airframes throughout the 1990s. They conducted high-speed research flights to gather critical aerodynamic data on thermal protection materials for future aerospace projects. That data directly informs the next generation of strategic reconnaissance. Lockheed Martin is currently developing the SR-72, intended to achieve Mach 6 flight using a turbine-based combined cycle engine.
A combined cycle engine integrates a traditional jet turbine for takeoff with a scramjet for sustained hypersonic speeds. Today, the surviving SR-71 airframes reside in museums around the world, sitting static so the public can examine the scale and complexity of the titanium panels up close. Kelly Johnson's team was handed a problem that the physics of the era said was impossible to solve. By approaching the thermal thicket from first principles, they created a blueprint for extreme velocity engineering that remains the